thanks for your attendance. I'm Patric from the University of Vienna. And during the next approximately 10 to 15 minutes, I would like to give you a short introduction in our research topic, identifying domain-based cyclic dependencies in microservice APIs. But before we dive deeper into this topic, I first would like to do a short recap about some very important key characteristics of microservices, which are of interest for the research. I think, as most of you know, one important aspect of microservices is their isolation. That actually means a microservice is an autonomous unit, which in the best case also has its own isolated bounding context with its own functionality. That's important so that we can develop the microservice independently and also deploy it without having any dependencies on other microservices. And of course, the maintenance is much more easier in this case. But still, we need communication between microservices. They have to exchange data. This communication is most of the time lightweight. That means we use, for example, REST, HTTP, or similar things. But there's one problem with the communication in general. It creates dependencies. So as soon as two microservices communicate with each other, they are not isolated anymore because they have to interchange data and depend on the interface of the other services. And there's one special case of dependency I would like to go a bit more in detail, that are cyclic dependencies. We generally speak of cyclic dependencies when we have one of the two given cases. One is a weak cycle. That would mean a communication path between two or more services starts at a specific endpoint and ends at a different endpoint, but still both endpoints belong to the same microservice. That would be a weak cycle. A strong cycle is has a stronger condition. That means the start and the endpoint of the communication are the same. That can be problematic because if you don't have any abort condition or anything in your communication, this could result in an endless loop. So as to say, cycles are a specific form of dependencies, and they can be problematic because if two microservices depend on each other in a cyclic dependency, they cannot be deployed independently anymore. And what is also a problem, these cycles make the system much more complex. So it's not so easy to reason about the communication between the services. What is a common solution? Using asynchronous communication. How does this work? In general, what we do is we remove the direct calls between microservices. So, for example, HTTP calls or also gRPC calls or similar, by using a more indirect communication like events or messages or a publisher-subscriber pattern. If we do this, our cohesion and coupling matrix would look much better because the dependencies are not explicit in the system anymore. But the problem we now have is the dependencies are not gone because now they are encoded in the messages that are transferred. So what we basically have done is we have shifted the dependency from the technical level, from direct service calls, up to a more domain-specific level. Because now the domain information is the problem that creates the dependencies. That's why you can speak here from domain-based cyclic dependencies. And that's even more problematic because it's relatively difficult to track this by using only static code analysis because the dependencies are not explicit. They are only implicit in the messages. And this already brings us to our research question, which is, would it be possible to identify these domain-based cycles in microservices by using only static source code analysis methods? And to investigate this, we were following the following approach here. First of all, what we did is in our research, we are focusing only on the API operations. So we say, okay, these are the central points of communication we really want to look into, and any other things like API interfaces also are only secondary for us. So the API operation is the important thing for our communication model. But what we also need to do is we need to identify important hotspots. That can be, for example, a specific type of communication that is used. Let's say an API operation calls a remote proxy that calls another API operation. So we need to identify these hotspots that are important for the communication. For this, we are using source code detectors. That is a technique I will describe shortly in the next slide. But the important thing is, after we have these API operations and the hotspots identified, we can then define some architectural metrics based on our communication model. And these metrics are something we can use to evaluate the cyclic communication. And what we did with our matrix then is we applied them on 2 open source case studies for verification and investigated, okay, did we find cyclic communication and how problematic was it and things like this. So let's have first a look at the source code detectors. Actually, what we've done here is we used a lightweight parser framework, which is a PyPathing. That's a Python implementation. And based on this technology, we implemented some very lightweight detectors that only look for specific patterns in code. So for example, here, and this is a small code example, what our detectors can do here is they can identify which technique is used. Here, that's a Spring Feign client. We can also check, okay, what is the endpoint address that is called here and which type of HTTP method is used. And this is much easier than using full-blown language parsers because you don't have to create and parse an abstract syntax tree, and also you don't, since languages can change quite often, microservices use different types of programming languages. It's much easier to use this lightweight approach here. So by using our detectors, what we are doing now is we are creating our communication model. This is in general a 4-step process. The first one I actually already mentioned. We are using our detectors to identify hotspots. As we can see here, these can be API operations or a specific communication technique that is used. In the second step, we are creating a call graph. That means we are doing a bottom-up approach and check, okay, we have this communication technique here, who is calling it? And we are doing this until we are reaching the API operations with the root elements in our call graph. And if we've done that, there's another step we have to do. We remove everything that is not important for us. So everything that we identified, which is not a hotspot, will be thrown away by doing a path reduction. And then we change the direction of our graph. That means now we are going just from the API operations straight down to our communication operations. And the fourth phase finally is relatively simple. Now we do the interconnections between the services. This can be done since our detectors have identified the endpoint addresses, for example, or the target addresses that are called, so we can map the APIs to the connection operations. By using this model, we were then able to define some metrics. The first 2 are relatively general. They are operating on a communication path in general. The first one is quite simple. If we apply this metric, it tells us if a communication path is either a cycle or not. We can also check if it's a weak or strong cycle, but that's something that which we are doing, but I have not presented this here. The first one simply tells us whether we have how many of our communication elements in our path are asynchronous or synchronous. So if we have a domain cycle ratio here of 1, that means all our communications are asynchronous and are based on domain messages. The next 2 metrics go a bit more in deep. They are operating on the API level. So the first one tells us if we have a given API operations, and this API operation has some outgoing connections, how many of these connections would finally result in a cycle. And the last one is similar. Here what we are doing is we are checking if the given API operation is some kind of important network hub that has a strong influence on the creation of these cycles. How this works is something we can see on the case study here. For our case study, we used, among others, the Lakeside Mutual project. That is a open source Microsoft reference implementation. And here in the example, we have 3 microservices: the customer self-service, the policy management, and the customer core service. And what's happening here is if we call this respond to insurance code API operation, we have 3 outgoing connection paths. And the important thing is that the receive customer decision we see in the bottom area, if this API operation receives the incoming event, it does 3 things. First of all, it just calls the get customer method synchronously. That's not a problem for us. The other things are more interesting because at some point in time, this API operation fires 2 additional messages: the policy created event and the insurance code expired event. which are then later on received by the customer self-service again. So this finally creates then two asynchronous cycles. That's why we have the cycle ratio here of 2/3 for the respond to insurance code, because we have in general 3 outgoing connections or connection paths, and 2 of them would result in a cycle. And since all cycles are asynchronous, we have a cycle ratio here of 1 for both, for the red and the blue one. And the other interesting metric is the cycle membership ratio here for receive customer decision. The interesting point here is because the API does not create any cycle, but it is involved in the creation of all cycles we've measured. So that obviously this seems to be an important network hub that has a strong influence on the communication. So that would be a point of interest for an architect, for example. What we still don't know here is whether these cycles are intended or maybe they're accidentally here, but that's not something our metrics can decide. But here a software expert or a software architect who knows the system has to take a look and decide, okay, whether that's intended or maybe the design has to be restructured. But at least our metrics can point him to specific points of interest so that he can see, okay, I didn't recognize that this API operation has such a strong influence. So to actually sum everything up, we have seen that asynchronous communication in microservices can lead to domain-based cycles. These cycles are relatively hard to track by static code analysis because they are very implicit in the code. So what we did is we used a technique we call source code detectors to reconstruct a API-based communication model. And based on this model, we finally defined some architecture metrics that we verified on 2 case studies. And that's already all from my side.